Chapter 8: Hydromechanical and Electromechanical Equipment. There are two types of hydraulic machines used in water recourses: engineering pump and turbine. A pump converts mechanical energy into hydraulic energy, while a turbine converts hydraulic energy into mechanical energy. Though most machines are single-purpose, there may be a reversible pump turbine which operates as a pump as well as a turbine depending upon the direction of flow. There are many types of pumps and turbines, and each type has its own characteristics. 8.1 Hydromechanical installation in powerhouse. 8.1.1 Types of turbines: Pelton, Kaplan turbines and their performance characteristics. Introduction to bulb turbine. These are mechanical machines to transform the water potential energy of flowing fluid into mechanical rotational energy. Turbines are called runners. The rotational energy is transformed to the generators through the power shaft, connecting rod and flywheel, to run the generator smoothly for electricity production. Turbines are developed form of water wheels and water mills used for ore crushing in flour mills, developed 400 to 500 years ago. Classification of hydraulic turbines based on nature of energy head possessed by water at inlet. Impulse turbine or velocity turbine. An impulse turbine is a turbine in which water entering the runner possesses kinetic energy only. It means the pressure is atmospheric at inlet and outlet of the turbine. E.g., Pelton turbine, turbo turbine. Reaction turbine. The turbine in which water entering the runner possesses pressure as well as kinetic energy is called reaction turbine. So, this type of turbine is always enclosed by airtight casing and runner and casing is completely full of water. E.g., Kaplan turbine, Francis turbine, Thomson turbine. Based on direction of flow: tangential flow turbine. 150. When the flow in the turbine is in tangential direction of rotation of runner, the turbine is called tangential flow turbine. E.g., Pelton turbine. Radial flow turbine. In this turbine, which water moves towards the axis of rotation of the runner or away from it. When the flow is towards axis, it is called inward flow turbine, Francis turbine. And when the flow is away from the axis of rotation, the turbine is called outward flow turbine, Fornieron turbine. Axial flow turbine. When water flows parallel to the axis of rotation, the turbine is called axial or parallel flow turbine. E.g., Kaplan turbine. Mixed flow turbine. In this type of turbine, water enters radially inward at inlet and discharges water at outlet in a direction parallel to the axis of rotation of the runner. E.g., Francis turbine. Based on head-low head turbine, 15 to 60 Kaplan turbine is used as low head turbine. Medium head turbine, 60 to 250 Francis turbine is used as medium head turbine. High head turbine, 250 Kaplan turbine is used as high head turbine. Based on specific speed: low specific speed turbine, Pelton turbine, 8 to 30, medium specific speed turbine, Francis turbine, 50 to 250, high specific speed turbine, Kaplan turbine, 250 to 850. 8.1.2 Specific speed, synchronous speed, and runaway speed. Characteristics of turbine specific speed. NS. Specific speed is defined as the speed at which machine produces 1 horsepower, HP, under 1 m head, N equals square root where N equals synchronous speed in RPM. 151. P equals power in HP. H equals head of the turbine M. Synchronous speed, N. Synchronous speed of turbine is defined as the rotational speed of turbine which is in synchronize with the frequency of the energy system to which it is connected. It means that the frequency of the energy system should be equal to frequency of each number of pole pair. Note that the number of pole pairs is always an integer. N equals Fn 60, i.e. N equals 60 Fn, where F equals frequency of generation, 50 Hz for Nepal, NP equals number of pole pairs of the generator. Runaway speed: if the external load on the machine suddenly drops to zero and the governing mechanism fails at the same time, the turbine will tend to race up to the maximum possible speed, which is known as runaway speed. Performance characteristics of turbines. The plot of behavior of turbines under different conditions is called performance characteristics of turbines. Behavior of turbines are indicated by the parameters like specific speed, efficiency, while working conditions are determined by load conditions, percentage opening of gate and unit head. Some characteristics curves are given below. 152. Bulb turbine. The bulb turbine is a variation of the propeller-type turbine, similar to the Kaplan turbine. In the bulb turbine arrangement, the generator is encapsulated and sealed within a streamlined watertight steel housing mounted in the center of the water passageway. The generator is driven by a variable pitch propeller located on the downstream end of the bulb. Unlike the Kaplan turbine, water enters and exits this unit with very little change in direction. The compact nature of this design allows for more flexibility in powerhouse design. Bulb turbines can, however, be somewhat more difficult to access for service, and they require special air circulation and cooling within the bulb. 8.1.3 Selection of turbines. The factors to be considered while selecting turbines are: available head and its fluctuation. Following criteria are followed while selecting turbines based on head. Very high head, H greater than 350 m Pelton turbine. High head, 150 to 350 m Pelton or Francis. Medium head, 60 to 150 m Francis turbine. Low head, 60 m Kaplan and Francis. Efficiency. The turbine that gives highest overall efficiency for various operating conditions should be selected. 153. Specific speed. High specific speed is required where head is low and output is large, else rotational speed will be low. That will lead to high cost of turbo generator and powerhouse. Rotational speed. Rotational speed depends upon specific speed, but in practice it should have higher value. Water quality. Quality of water is more important for impulse turbine than reaction turbine. Maintenance. Impulse turbine has less cost of maintenance than that of reaction turbine. Deposition of turbine shaft. Vertical shaft arrangement is better for large-sized turbine, it is universally adopted. But in case of large-size impulse turbine, horizontal shaft arrangement is almost employed. 8.1.4 Design of Francis and Pelton turbines. Pelton turbine. Pelton turbine is a tangential flow impulse turbine. It is used for high heads. The water strikes the bucket along the tangent of the runner. The energy available at the inlet is only kinetic energy. 154. Components of Pelton turbine. Nozzle and flow regulating arrangement. Nozzle directs the flow into the buckets. The amount of water striking the buckets is controlled by providing a spear in the nozzle. The spear is a conical needle operated in the axial direction. When spear is pushed forward into the nozzle, the amount of water striking the jet is reduced and vice versa. Runner and buckets. Runner consists of a circular disc on the periphery of which a number of buckets evenly spaced are fixed. The space of the buckets is of a double hemispherical cup or bowl. Each bucket is divided into two symmetrical parts by splitter which divides jet into two equal parts. The buckets are shaped in such a way that angle of deflection is 1600 or 1700. Casing. The function of casing is to prevent the splashing of water and to discharge water to tail race. The casing of Pelton turbine does not perform any hydraulic function. Braking jet. When the nozzle is completely closed by moving spear valve, the runner still tends to rotate due to inertia. To stop the runner in a short time, a small nozzle is provided which directs the jet of water on the back of vanes. This is called braking jet. Components of Pelton turbine. Design parameters of Pelton turbine. Suppose D equals diameter of the runner will D equals diameter of jet nozzle, W equals width of the bucket, N equals design speed. 155. NS equals specific speed. Velocity at inlet, V1 equals C2GH, where CV is coefficient of velocity, 0.98 to 0.99. Tangential velocity to will, i.e. velocity of jet, V equals 2GH, where phi is speed ratio. 0.43 to 0.48, assume the general value of deflection of jet through bucket to be 1650, in case of not provided the mean diameter or pitch diameter of the Pelton will is given by V equals IED equals as V equals 2GH, then V equals, thus, phi equals dot square root jet ratio, M, is generally taken from 10 to 15 number of buckets on a runner is given by N equals 15 plus working proportional, axial width of the bucket, B equals 3D to 4D radial length, L equals 2D to 3D. Depth, T equals 0.8 d to 1.2 d. Spacing of bucket is given by equals number of jet is obtained by dividing the total rate of flow through the turbine by the rate of flow of water through a single jet. Francis turbine. Francis turbine is an inward mixed flow reaction turbine. In this turbine, water under pressure enters the runner from the guide vanes toward the center in radial direction and discharge out of the runner axially. The Francis turbine operates under medium head. Francis turbine. 156. Components of Francis turbine. Spiral casing. Spiral casing, also known as scroll casing or volute casing, encloses the turbine and its components into airtight compartment. Throughout its length, it has numerous openings at regular intervals to allow the working fluid impinge on the blades of the runner. The cross-section area of the casing decreases uniformly to ensure a constant flow rate at any point of inlet. Stay vanes and guide vanes. Water entering into the scroll casing first encounters series of stationary vanes called stay vanes. Stay vanes divers and flow directed towards the runner blades. Guide vanes are the movable vanes that further direct the flow at design angle to the runner blades. Guide vanes also control the amount of discharge striking the blade. Runner is a circular wheel on which series of radial curved vanes/blades are fixed. The surface of the vane is made smooth. The radial curved vanes are so shaped that the water enters and leave the runner without shock. Draft tube. A tube or pipe of gradually increasing area that is used for discharging water from exit of the turbine to the tail race is called draft tube. It is discussed in detail in later section. Design parameters of Francis turbine. The ratio of width of the wheel to the diameter is given by n equals, where value of n is from 0.1 to 0. For the flow ratio is given by c equals, where cm is 0.15 to 0.3 and vi is velocity. At inlet tip, the speed ratio is given by phi equals, where v is peripheral velocity of flow and the values of speed ratio is 0.6 to 0.9. The diameter of turbine is given by d equals dot square root, where phi equals 0.0197 n plus 0.0275. Design parameters of Kaplan turbine. The peripheral velocity at inlet and outlet are equal, given by u equals, where d0 equals outlet diameter of runner. 157. Area of flow at inlet equals area of flow at outlet equals d minus d, where db is diameter of boss discharge through the runner. Q equals vd minus d, where v is mean velocity at inlet, which is equal to velocity at outlet. Diameter of turbine is given by d equals dot square root, where phi equals 0.0242 n. 8.1.5 Scroll case, draft tube and tail race canal and their importance. Draft tube. The pressure at outlet of Francis turbine is generally less than atmospheric pressure. So, the water cannot be directly discharged to the tail race. Hence, a tube or pipe of increasing cross-section is used for this purpose. This tube is called draft tube. One end, inlet, of draft tube is connected to the outlet of runner and another end, outlet, is submerged below the level of water in the tail race. The major functions of draft tube are, it permits a negative head to be established at the outlet of runner and thereby increase the net head of the turbine. The turbine may be placed above the tail race without any loss of net head and hence turbine may be inspected properly. The draft tube helps to recover velocity head of the water out of the runner, i.e. the kinetic energy rejected at the outlet of the turbine is converted into useful pressure energy. Types of draft tube. The various types of draft tube are shown in the figure below. 158. Type of draft tube. Draft tube theory. Consider a turbine fitted with a draft tube through which water flows. Let's consider two sections, section 1 to 1 at runner exit and section 2 to 2 at draft tube exit, which is at a depth y below the level of the tail race. Then pressure at section 2 to 2 will be P gamma equals P gamma plus y. Now applying Bernoulli's equation between section 1 to 1 and 2 to 2, considering section 2-2 as datum P gamma plus V2G plus y equals P gamma plus V2G plus 0 plus h, where h represents the head loss in the draft tube. P gamma equals P gamma minus y plus V2G minus V2G plus h. P gamma equals P gamma minus Y minus V minus V2G minus H. Now put the value of P in the equation. P gamma equals P gamma plus Y minus V minus V2G minus H. P gamma equals P gamma minus Y minus V minus V2G minus H. The term Y minus Y represents the vertical distance between the runner exit and the tail water level, which is also called suction head of draft tube. P gamma equals P gamma minus HS minus V minus V2G minus H. It shows that the pressure at runner exit is below atmospheric. Theoretically, the recovery of kinetic head due to velocity changes in the draft tube equals. If H is friction loss, then actual regain of pressure head becomes minus H. 159. The efficiency of draft tube is the ratio of actual conversion of kinetic energy into pressure head in the draft tube to the kinetic head at the inlet of the draft tube. Eta equals minus H / frictional loss is generally expressed as K, then. Eta equals minus K / eta equals 1 minus K / in order to increase the vacuum pressure, the exit velocity at the outlet of the draft tube and head loss should be minimum as much as possible. The suction head is calculated such that pressure at the outlet of the runner should not reach to the vapor pressure, otherwise cavitation will occur and may damage the runner blade due to its fatigue action. If the velocity of flow at the outlet of the runner is much, which may be in the case of the fast-moving runner, then it may be necessary to take the suction head as negative value, i.e. the turbine runner may be below the water surface to keep the pressure at the outlet of the runner below the vapor pressure. Cavitation. We know that the velocity of flow at the outlet of turbine is high and pressure is low. If the pressure at the outlet of the turbine is less than the vapor pressure of water, then the cavitation occurs. Cavitation is a phenomenon in which rapid changes of pressure in a liquid lead to the formation of small vapor-filled cavities, in places where the pressure is relatively low. When subjected to higher pressure, these cavities, called bubbles or voids, collapse and can generate shock wave that is strong very close to the bubble, but rapidly weakens as it propagates away from the bubble. Cavitation causes the wear and tear of the turbine blades, thus reducing the efficiency. Tail race canal. Tail race canal is the canal in which water is discharged after passing through the turbine. If the powerhouse is close to the stream, the outflow may be discharged directly into the stream. The tail race canal should be designed in such a way to have non-silting and non-scouring and the minimum head loss. 8.2 Electromechanical installation. 8.2.1 Introduction to generator and their types. Generators transform mechanical energy into electrical energy. Although most early hydroelectric systems were of the direct current variety to match early commercial. 160. Electrical systems. Nowadays only three-phase alternating current generators are used in normal practice. Depending on the characteristics of the network supplied, the producer can choose between synchronous generators. They are equipped with a DC electric or permanent magnet excitation system, rotating or static, associated with a voltage regulator to control the output voltage before the generator is connected to the grid. They supply the reactive energy required by the power system when the generator is connected to the grid. Synchronous generators can run isolated from the grid and produce power since excitation is not grid dependent. The synchronous generator is started before connecting it to the mains by the turbine rotation. By gradually accelerating the turbine, the generator must be synchronized with the mains, regulating the voltage, frequency, phase angle, and rotating sense. When all these values are controlled correctly, the generator can be switched to the grid. In the case of an isolated or off-grid operation, the voltage controller maintains a predefined constant voltage, independent of the load. In case of the mains supply, the controller maintains the predefined power factor or reactive power. Asynchronous generators. They are simple squirrel cage induction motors with no possibility of voltage regulation and running at a speed directly related to system frequency. They draw their excitation current from the grid, absorbing reactive energy by their own magnetism. Adding a bank of capacitors can compensate for the absorbed reactive energy. They cannot generate when disconnected from the grid because they are incapable of providing their own excitation current. However, they are used in very small standalone applications as a cheap solution when the required quality of the electricity supply is not very high. 161. 1. Generator rotor 2. Winding of generator rotor 3. Brush connection 4. Contacting disc 5. Winding of generator stator 6. Resistance 7. Spider 8. Pole 9. Stator 10. Slut for the winding. To achieve the current with frequency of 50 Hz, it is necessary to provide the number of poles at the rotor of the generator. Frequency equals speed of the runner x number pair poles / 16 of poles are calculated from poles all the poles equals 120 f / n equals 6000 / n number of pair poles equals set of pair pole n pair poles equals 60 f / n equals 3000 / n. 8.2.2 Working principle of governors in Pelton and Francis turbines. Turbines are designed for a certain net head and discharge. Any deviation from these parameters must be compensated for by opening or closing the control devices, such as the wicket gates, vanes, spear nozzles or valves, to keep either the outlet power frequency constant. In schemes connected to an isolated network, the parameter that needs to be controlled is the turbine speed, which controls the frequency. If the generator becomes overloaded, the turbine slows down, therefore an increase of the flow of water is needed to ensure the turbine does not stall. If there is not enough water to do this, then 162. Either some of the load must be removed or the turbine will have to be shut down. Conversely, if the load decreases, then the flow to the turbine is to be decreased. A governor is a combination of devices and mechanisms, which detect speed deviation and convert it into a change in servomotor position. A speed sensing element detects the deviation from the set point. This deviation signal is converted and amplified to excite an actuator, hydraulic or electric, that controls the water flow to the turbine. In a Francis turbine, where there is a reduction in water flow, you need to rotate the wicket gates. For this, a powerful governor is required to overcome the hydraulic and frictional forces and to maintain the wicket gates in a partially closed position or to close them completely. In a modern electrical hydraulic governor, a sensor located on the generator shaft continuously senses the turbine speed. The input is fed into a summing junction, where it is compared to a speed reference. If the speed sensor signal differs from the reference signal, it emits an error signal, positive or negative, that, once amplified, is sent to the servomotor so this can act in the required sense. Schematic diagram of a mechanical governor. 8.3 Pumps are mechanical devices which converts mechanical energy supplied to it from the external source into hydraulic energy. Almost all the pumps increase the pressure energy of the liquid, which is subsequently converted into potential energy as the liquid is lifted from a lower level to higher level. The pumps can be broadly classified into two groups: A. Reciprocating, positive displacement, pumps; B. Centrifugal, rotodynamic, pumps. 163. 8.3.1 Introduction to centrifugal and reciprocating pumps. Centrifugal pump. A centrifugal pump is a mechanical device designed to move a fluid by means of the transfer of rotational energy from one or more driven rotors, called impellers. Fluid enters the rapidly rotating impeller along its axis and is cast out by centrifugal force along its circumference through the impeller's vane tips. The action of the impeller increases the fluid's velocity and pressure and also directs it towards the pump outlet. The pump casing is specially designed to constrict the fluid from the pump inlet, direct it into the impeller and then slow and control the fluid before discharge. Working principle of centrifugal pump. The impeller is the key component of a centrifugal pump. It consists of a series of curved vanes. These are normally sandwiched between two discs, an enclosed impeller. For fluids with entrained solids, an open or semi-open impeller, backed by a single disc, is preferred. Fluid enters the impeller at its axis, the eye, and exits along the circumference between the vanes. The impeller, on the opposite side to the eye, is connected through a drive shaft to a motor and rotated at high speed, typically 500-5000 rpm. The rotational motion of the impeller accelerates the fluid out through the impeller vanes into the pump casing. There are two basic designs of pump casing, volute and diffuser. The purpose in both designs is to translate the fluid flow into a controlled discharge at pressure. In a volute casing, the impeller is offset, effectively creating a curved funnel with an increasing cross-sectional area towards The pump outlet. This design causes the fluid pressure to increase towards the outlet. The same basic principle applies to diffuser designs. In this case, the fluid pressure increases as fluid is expelled between a set of stationary vanes surrounding the impeller. Diffuser designs can be tailored for specific applications and can therefore be more efficient. Volute cases are better suited to applications involving entrained solids or high viscosity fluids when it is advantageous to avoid the added. 164. Constrictions of diffuser vanes. The asymmetry of the volute design can result in greater wear on the impeller and drive shaft. Priming of centrifugal pump. The process of filling the pump with liquid is called priming. If the pump casing becomes filled with vapors or gases, the pump impeller becomes gasbound and incapable of pumping. To ensure that a centrifugal pump remains primed and does not become gasbound, most centrifugal pumps are located below the level of the source from which the pump is to take its suction. Reciprocating pump. Mechanism of reciprocating pump. Reciprocating pump is a positive displacement pump where certain volume of liquid is collected in enclosed volume and is discharged using pressure to the required application. Reciprocating pumps are more suitable for low volumes of flow at high pressures. Working principle of centrifugal pump. When the power source is connected to crank, the crank will start rotating and connecting rod also displaced along with crank. The piston connected to the connecting rod will move in linear direction. If crank moves outwards, then the piston moves towards its right and create vacuum in the cylinder. This vacuum causes suction valve to open and liquid from the source is forcibly sucked by the suction pipe into the cylinder. 165. When the crank moves inwards or towards the cylinder, the piston will move towards its left and compresses the liquid in the cylinder. Now, the pressure makes the delivery valve to open and liquid will discharge through delivery pipe. When piston reaches its extreme left position, whole liquid present in the cylinder is delivered through delivery valve. Then again the crank rotate outwards and piston moves right to create suction and the whole process is repeated. Thank you.